interest of keeping closer to the schedule, we'll go ahead with the next presentation talking about the residual strength of liquefied soil, a very important topic in geotechnical earthquake engineering practice. We talked before about the kind of steady state framework, which came about as a result of the work that Gonzalo Castro did for his PhD work at Harvard, working under Arthur Casagrande. And Castro was the first one to really perform a logical, methodical investigation of the undrained behavior of liquefiable soils under monotonic loading conditions, static loading conditions. And so he performed a series of tests where he looked at very loose soils, and he saw what we now come to expect, that we build up high pore water pressures and reach a peak resistance, after which the pore water pressure builds up quickly to high levels, so we end up at a steady state, which hadn't been named yet, at a very low effective stress. And so in terms of stress strain behavior, we see a peak shearing resistance and a low strain, followed by flow under stress controlled conditions out to large strain levels. He also tested denser soils, and he found that they would tend to dilate, and they would exhibit ductile strain hardening behavior. And to the limits of his testing equipment, he would take these out to relatively large strains and see eventually that the stiffness would start to decrease. He also tested intermediate density soils and saw a behavior that he referred to as limited liquefaction, where the soil would exhibit a peak shearing resistance again at low strains. The shearing resistance would then decrease to what we now call a quasi-steady state, at which point it would then start to increase its shearing resistance. And that point occurred right around the elbow in the stress path here, where we see phase transformation behavior occurring, and the soil would dilate and it would stiffen up because the effective stresses were stiffening up, and it provided the data with which the steady state framework was really developed. So the steady state of deformation, as formally defined, represents a condition where the soil is shearing at constant volume with a constant effective stress, and a constant shearing resistance, and a constant velocity or a constant strain rate. So these are very specific conditions that we can see in the laboratory because we're making careful measurements of the things that go on. Out in the field, however, the conditions are different. The steady state in the laboratory would exist at these points in the very loose test. It would exist at this point where we have a constant shearing resistance in the moderately dense sample that exhibited limited liquefaction, but we may not have gotten there in the dilation test, the very dense test. And so eventually we expect that we should get to a steady state of deformation, but it may be at a very high shearing resistance in a dense soil that dilates. As it dilates, the pore pressure goes down, the effective stress goes up, and we may have a very high strength under undrained conditions there. So the steady state strength is mobilized at very large strain levels. All of the fabric that can influence the behavior at smaller strain levels is erased by the time we get out to 20, 30, or more percent shear strain, where the steady state is achieved. Now, one proposal for the behavior of steady state strength is that the steady state line is parallel, at least when we plot it on a semi-logarithmic plot, to the consolidation curve for a sand. If that's true, then the steady state strength should be proportional to the vertical effective stress. The state parameter would be constant, no matter what the effective stress was. That would imply that we would have a constant level of contractiveness as the effective stress increased, because our soil would consolidate to lower void ratios, but the steady state line would move by the same amount. And so we should expect a soil at a high effective stress to have the same level of contractiveness as a soil at a low effective stress. Ishihara and Yoshimine prepared a plot that's very helpful, I think, in understanding behavior. They were distinguished between what they call the ultimate steady state, which is what we normally refer to as a steady state, that which is reached out at very large deformations. But when the soil shearing resistance drops down, it reaches what they refer to as a quasi-steady state, because instantaneously at the bottom of that stress-strain curve, the soil would have a constant shearing resistance. It won't have it for long because it will start to dilate after that point. So if we look at an element of soil at point A on a consolidation curve, when it's sheared, it's going to contract, and the shearing resistance will go down, the effective stress will go down until it reaches the quasi-steady state, and then it will dilate until it reaches the ultimate steady state. In terms of the ultimate steady states given by the red line. And so the phase transformation behavior is going to look like this. The point is initially below the ultimate steady state line, so it's a dilated soil. It will contract initially, then it will turn around and start to dilate. And so we'll see the stress strain curve building up. We reach the phase transformation point. The soil softens because its effective stress is decreasing, but then it starts to dilate and it stiffens up and moves to the ultimate steady state. We see the behavior of the stress path here. It's contractive until it reaches the phase transformation point, and then it dilates and the effective stress increases. If we look at a soil that's consolidated to a higher effective stress, now it's at point B. It's above the ultimate steady state line, so we expect it to be contractive. It will contract, and the pore pressure will build up. The effective stress will decrease until we reach the quasi-steady state line, at which point phase transformation occurs and it starts to dilate, and it dilates back to the ultimate steady state line. And so we'll see here that we reach a peak shearing resistance, after which the shearing resistance drops until we reach the quasi-steady state. That occurs at the phase transformation point, and the soil then dilates up to the ultimate steady state line. As it dilates, it becomes stiffer, and then eventually it softens and reaches a constant shearing resistance. For a very contractive soil, wow, mouse is here. For a very contractive soil at point C that's well above the ultimate steady state line, the quasi-steady state line and the ultimate steady state line merge together. And so the soil is contractive, and it's only contractive. It never dilates because there is no quasi-steady state line. And so the stress strain curve for this case is not coming up. Sorry about this. Okay, there it is. Try to use my mouse instead of the touchpad. So we'll start at point C. We reach a peak shearing resistance and a low strain level, and then the soil just contracts, and eventually it reaches the critical state or steady state line. It's contractive, 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 and it continues contracting until it reaches this critical state point. And so if we look at the state parameter is going to be the difference between the steady state, the consolidation point ratio and the steady state point ratio. So we're below the steady state line. We have a negative state parameter. So it's dilated. When we move to the right side here, now as the soil consolidates, it's going to be on the blue curve. The steady state parameter is the vertical distance between this point and the steady state point. We have a positive value. We have a more positive value as we go to a higher effective stress. This is probably exaggerated compared to the way real soils behave in the laboratory, but it shows us that our steady state line is generally somewhat steeper than the consolidation curve, which means that as we go to higher and higher effective stresses, these curves become farther apart, the state parameter increases, the soil becomes more contracted. This is why we have terms like K sigma in our liquefaction procedures. So we get an increasingly positive state parameter, the soil becomes more contractive as we go to higher and higher effective stresses. Okay? And the reason is the steady state strength doesn't increase as fast as the effective stress does. So how do we measure this? We can measure it in a triaxial test, in a laboratory, a simple shear test, or a ring shear test. They all have advantages and they have some limitations. The limitations generally come from non-uniformity of stresses and strains that we reach in all of these pieces of equipment at large strain levels. So the resulting strengths are difficult to determine. If we look at some of the data that we've seen before, here we have a series of samples at different effective stresses, but essentially at the same relative density of 40%. We can see that for the highest confining pressure, our sample is exhibiting a strain softening behavior. We reach a peak at low strains, it drops off to a quasi-steady state, and then the soil dilates a little bit. So we come up to this point. So we've got a peak strength, and we have a quasi-steady state, and we can ask whether we've reached the ultimate steady state at that point. If we just extend our curve horizontally, that looks like a pretty continuous curve, but maybe it looks more like this. Maybe it's somewhere in between. It's difficult to know for sure. So if you take a triaxial sample out to, say, 30% strain, we're probably pretty close to the steady state condition, but we don't necessarily know for sure. We tried to look at this by building a new type of device. We call it a ring simple shear device. And a simple shear device, we're taking a disc of soil and we're shearing it, and we have a tendency to pinch the soil in the acute corners, and that leads to a non-uniformity of stress and strain conditions, which makes the resulting shear stresses difficult to interpret. We can use ring shear testing where we can get to large strains, but the stresses aren't uniform in a ring shear test, and the strains are very non-uniform. And so we may have dilation occurring on the thin failure plane between the rings that's being accommodated by compression of the soils above and below that. So we built a device that we call a ring simple shear device, and it consists of two stacks of rings, an outer set of rings and an inner set of rings. They are about 2.5 inches thick, so that would be about, 10 centimeters or so? Less than 10 centimeters, about 8 centimeters or so thick. There are 10 of them. They're ground and polished, and there's a dry lubricant placed on it, so they slide very easily with respect to each other. The outer diameter of the inner ring is 13 inches, so 33 centimeters or so. The inner diameter of the outer rings is about, it's a little bit bigger than that, about 2.5 inches as well. I'm not very good on my quick conversions. Soil is placed between these two stacks of rings, and the rings you can see sitting in here between an upper and a lower plate. We apply a vertical stress to the top of the soil, and then we apply torsion. And so the top part is fixed, the bottom part is turned by this gear system. There's a load cell that measures both the axial load and the torque that's being applied. We take our sample and put a strip of tape, here electrical tape, and we cut it with a razor blade so that we can see how these rings are moving with respect to each other. At the beginning of the test, the tape is vertical, there's no offsets, and we start applying a torque to the sample. And as we do that, we see that the rings start to move. We also have some internal columns of modeling clay that we can dissect after the test has been performed to see how uniform the stresses are, or the displacements are, and they tend to match very well with what we're seeing on the outside of the sample. So here we have 8% shear strain, and the strain is pretty uniform from top to bottom. Here we have 41% shear strain. This is a lot more shear strain than we're getting, certainly we get in a regular simple shear test. It's more uniform than we can get in a ring shear test, and it's a greater level of strain than we can achieve typically in a triaxial test. If we continue, now we're at 69% shear strength. And their strains are still pretty uniform from top to bottom throughout this sample. We can go on further, and then we start to see some non-uniformities. We can set 3 segments that are touching the corners of these tapes. So we're somewhere between 100 and 160% shear strain or so at different levels. Eventually, we start to get a bifurcation, and we'll see all of our strains accumulating on one plane here, typically at the top, near the top of the sample. But we can compute a stress strain curve and a stress path from this. And what we see is we reach a peak shearing resistance of about 2% strain, which is similar to what we see in a triaxial test. The shearing resistance decreases down to 8 to 10% strains or so, but it takes a very large amount of strain to fully mobilize the residual strength. We see in the lower plot, we see contractive behavior, and the soil is contractive with a reducing or a dropping effective stress, or normal stress, all the way out to this level, at which point it turns around and starts to dilate. And it dilates up the failure surface and eventually shears at a constant shearing resistance and a constant effective stress level. So we believe we've reached the steady state out here, and we've done it at a much larger strain and with more uniform conditions than we can get in other types of tests. When we build samples different ways, by moist tamping and by dry pluviation to give them different fabrics, we see that we get different behaviors at low strain levels, where the fabric is still intact and where it still makes a difference. And so our moist tamped soil has a higher shearing resistance, a higher peak resistance. It drops down and it goes up and dilates. Our dry pluviated sample has a lower shearing resistance. It drops down to a quasi-steady state and then starts to dilate. So we see significant differences in behavior at low strains due to the differences in fabric, as we would expect. When we get out to very large strains, we see them behaving much more similarly, as we would expect, as the effects of that fabric are reduced out of these large shear strains of greater than 100%. Now, that's steady state strength. What happens out in the field when a flow slide occurs? When a flow slide occurs, we get very large deformations in real soil deposits, not a clean, uniform sand like we were testing in the laboratory. So we have a whole bunch of things going on that are different than the conditions of the steady state of deformation. Steady state required a constant effective stress. We may or may not have that in a flow slide in the field. The geometry of that flow slide is changing. The stresses are going to be changing as the material flows. We don't necessarily have a constant shearing resistance. We don't necessarily even have a constant material, because different materials can get mixed together in a flow slide that occurs out in the field. We certainly don't have a constant strain rate, because the flow slide is going to accelerate and then decelerate. So a lot of different things are going on in a real flow slide. And so to be able to predict the strength that the soil is going to mobilize in a real flow slide becomes a difficult problem. We recognize that it's not the steady state strength that's mobilized out in the field, it's something different. And we tend to call that a residual strength, and we obtain it by back calculating the apparent shear strength from flow slide case histories. And so Harry Seed was the first one to do this in 1987, and he produced a band of possible shear strengths as a function of the SPT resistance of the soil. It predicts a residual strength just as a function of the standard penetration resistance. Several years later, Ray Seed and Les Harder acquired and interpreted some additional case histories, improved the database, and they came up with modified versions that are shown by the darker solid line. Ed Idris used a single curve based on pretty much the same data, and it's plotted with the dashed line here. So these are the procedures that were available in the early stages. There's Seed's original, here's Seed and Harder, and Idris is shown in red. There's a lot of variability here. If we have a standard penetration resistance of 10 blows per foot, use the seed harder, we would get residual strengths anywhere from 0.04 to 0.25 atmospheres, a factor of 6 difference from the lowest range to the highest range. In practice, people would use about the lower 1/3 point to have some conservatism, and that's pretty consistent with the way Idris's curve turned out to behave. After that, the idea of a normalized strength approach was taken. I described the normalized strength earlier. It assumes that the steady state line, and at least in a clean sand, the steady state line and the consolidation curve are parallel to each other, so it recognizes that as the effective stress increases, the soil becomes denser. It assumes that it does that in proportion. And so Stark and Mesri came up with the first relationship. I'm just showing a colored-in curve for a atmospheric pressure, for effective stress of 1 atmosphere. And so they had a fairly low strength that they were predicting. Scott Olson, working with Tim Stark, came up with a modified version that produced significantly higher strengths. And for 1 atmosphere of vertical effective stress, his relationship would predict this value. Idris and Boulanger used much the same data, although they eliminated some of the data that they didn't feel was reliable, and came up with this curving version. So at 1 atmosphere, it's very close to Stark and Mesri, but it curves up more as we get to higher SPT resistances. There's not a lot of data. Olson produced the largest database. He had 33 case histories. Some of them are well documented, about 10 of them are very well documented. The rest are not. Some of them are very poorly documented. Some of them didn't have measured static penetration resistances. They've been estimated. So there's a great variation in the quantity and quality of data associated with these case histories, which makes it difficult to develop these kinds of models. The normalized strength approach tends to predict very high residual strengths at large depths. It can predict very low residual strengths at shallow depths. If the residual strength is assumed to be proportional to the vertical effective stress, close to the ground surface, the vertical effective stress is low, so the residual strength is going to be a small fraction of that typically. It predicts flow slides where we have not seen flow slides occurring in the field for these very shallow depths. Development of flow slides is influenced, or can be influenced, by the effects of what I referred to in answering the question earlier as void redistribution. When we build up high pore pressures during earthquake shaking, those pore pressures, the excess pore pressure, the pore pressure above hydrostatic, produces hydraulic gradients, which cause water to flow. It's going to flow from high total head to low total head. And as it flows, the effective stresses are going to change in the soil. As the effective stresses change, the volume of the soil will change. So if the pore pressures in a body of a liquefiable soil profile dissipate by upward flow, which they often do, they may encounter a layer of lower permeability material, the kind of layer that Professor Seed talked about in his 1979 paper that Professor Bray quoted from. When the water comes up and hits that boundary, it's not going to be able to flow past it. It's a silt layer, say, with a low permeability. And so the pore pressure will increase, the effective stress will decrease, and the soil will tend to rebound. Its volume will decrease. It's now more consolidated. And as it rebounds, as its void ratio increases, its position relative to the steady state line will change, and it will become weaker. So as the void ratio increases, it would move to a new place on the steady state curve with a lower strength, and that can lead to a delayed failure with that reduced effective stress strength. One of the difficulties is, as its density changes due to this void redistribution, the strength is not the strength that we would obtain from its measurement of its pre-earthquake density. So a number of people have performed tests. The first was Takaju Kokoshu in Japan. And Kokoshu built a model on a shaking table. So he had a 1G shaking table. He built a model of a sand slope, but he placed a layer of silt, a low permeability silt within his model. And he shook it, instead of shaking it in an upslope, downslope direction, he shook it perpendicular to that, parallel to the strike of the slope. And so the inertial forces due to shaking didn't change the driving or resisting stresses in the slope. They just built up pore water pressure. And they built up pore water pressure, and he has a video which I haven't been able to find available that shows water flowing up towards this silt layer after the shaking had stopped. And the slope remained stable for 20 or 30 seconds or so. There's no inertial forces, but the water is moving. And when the water reaches the bottom of that silt layer, the water pressure builds up, it tends to accumulate, and then, well after the shaking is ended, the slope fails very suddenly. Idris and Boulanger did the same thing. I think it was Bruce Cutter and Ross Boulanger that did this, and they built a model with some layers of silt in it, low permeability silt. They had lots of pore pressure transducers. They had accelerometers so they could measure what was happening, and they saw the same type of behavior. They shook it, pore pressures built up, the ground motion stopped, their input motion stopped, waited a few minutes, and the water was moving, and eventually a flow slide occurred. But it occurred statically, without any inertial forces tending to drive that failure, and it occurred in a delayed fashion after earthquake shaking had ended. So they observed in their video cameras pore water accumulating beneath this curving silt layer. And water can actually accumulate and form a water interlayer below an impermeable boundary like this. So the failure occurred on a discrete failure surface. So Idris and Boulanger, in developing their residual strength predictive relationship, came up with two curves, one of which represents the conditions that they would expect, or the strength they would expect in the absence of void redistribution, if void redistribution didn't occur, and the other was to be used for cases where void redistribution did occur. And so this requires the user of this model to make a decision as to whether they think void redistribution is likely or unlikely. So we looked at this problem and tried to separate the case histories where we thought void redistribution was likely to have occurred from those where we didn't think void redistribution was likely to have occurred. And we did a statistical analysis, and we found that they were all the same. There would be our judgment, at least, as to whether or not void redistribution would occur due to the presence or absence of a capping layer of low permeability material. It didn't matter. Had no influence. And the conclusion, our general conclusion, is void redistribution occurs in all of these flow slide failures because we have interlayered deposits of the type that Professor Bray showed. On a small scale, there's almost always some interlayering between coarser and finer grained materials. They're generally deposited in water. The coarse particles settle out first, the finer particles settle later. So you have bands of coarser and finer materials, higher and lower permeability. And so in practice, people will almost always, when they're using Idris and Boulanger's procedure, they'll almost always use this lower one. It would be risky to use the upper one, even though in the laboratory in a confined, under controlled conditions, you might see that kind of behavior occurring. There are other approaches that have been taken that attempt to model the soil mechanics a little more accurately, recognizing the kind of increased density that we get with increased depth, but not restricting the apparent steady state line to be parallel to the consolidation curve. So one of my students made up a model this way, and it shows behavior that increases with residual strengths that increase with increasing effective stresses, but not in a proportional manner. One of Ray Seed's students, Joseph Weber, developed independently a similar type of model that gives very consistent results in general. It shows also an increase in residual strength with increased confining pressure that is not proportional. It doesn't increase in direct proportion. So these are similar. We interpreted some case histories, we had a different philosophy and different resources than they did. So there's differences in our approaches. They're not large differences, but they are differences. Both of us attempted to characterize the uncertainty in residual strength predictions, because that's often a critical part of a stability investigation. We have a lot more uncertainty than they have, and I believe very strongly that our uncertainty is more representative of the uncertainty that exists compared to what they are showing. But their median values and mean values are similar to each other. If we compare our procedure, for example, with Olson and Stark and Anderson-Boulanger, we also consider the conditions under which we see lateral spreads occurring rather than flow slides. And that leads to a higher residual strength prediction if we make sure that we're not predicting flow slides under shallow conditions where we actually see lateral spreads occurring. And it helps lead to that, and the deviation of the steady state and consolidation curves leads to the curvature that we see here. So we will predict generally higher residual strengths at low confining pressures, similar strengths at intermediate confining pressures, but at high confining pressures, our procedures will predict lower residual strengths because we are accounting for an increased contractiveness under those kinds of conditions. So current status for prediction of residual strength of the soil that has liquefied, there's a lot of uncertainty. There's just no getting around it. The case histories are poor. In general, they're scattered. There's a lot of room for interpretation. Different people have taken different approaches and interpreted these case histories differently. It's common to use a weighted average of the available procedures, and the four primary procedures are the ones shown here. Individuals can decide how they want to weight them. I am partial to the Kramer-Wang procedure, and I think Weber-C is also good. I think they're both more consistent with the soil mechanics behavior than the others, but that's a decision that individuals would make. So the steady state concepts are very useful to understand the factors that affect the shear strength of liquefied soils at very large strain levels. The steady state is reached at very large strain levels, larger than we realistically can measure in the laboratory. The steady state represents a very specific set of conditions that don't exist out in the field. Steady state lines, we should note, are pretty flat. And so the steady state strength is quite sensitive to the density of the soil. It doesn't take much change in density to cause a big change in the steady state strength. If the void ratio increases a little bit, we have a very large reduction in the strength of the soil. The most reliable estimates that we can make of shearing resistance at this point are based on back calculation of case histories. The back calculated strength is influenced by a lot of factors that aren't related to the characteristics of the soil itself. So we shouldn't think that the residual strength that we obtain this way is a property of the soil. It's really a property of the system at a particular case history. That's the best we can do at this point. And so we should keep that in mind as we use these things. Flow slide case history database is limited in both quantity and quality. There's a lot of uncertainty as a result of that. There are two models that have attempted to characterize that uncertainty. So I'll move from there. Are there questions on residual strength estimation? There aren't. You're not allowed to ask a question.
You should offer your opinion on cases where the N160 leak stand is slightly greater than 16.
The database goes out to N160 values on the order of 15, maybe as close as 16, depending on how they're interpreted by the different people. Sometimes it's not uncommon to have to make an estimate of what the residual strength would be at higher levels. Let me pull that back up again and go to a figure that shows some of the data. Anderson-Boulanger has the the data plotted. And so you can see here that they have data out to about 15. Sonic penetration resistance is 15 blows per foot. If we're dealing with materials that are out at higher levels, these curves tend to curve upward. And if we just use soil mechanics and assume that we have a steady state condition, they curve upward very quickly. They start to increase quite quickly, more quickly than the case histories indicate. So the question then becomes, how do you extrapolate to, say, a blow count of 17 or 18 or even 20? Should we use a cap on the residual strength, or can we extrapolate them according to some relationship? The answer to that, in my opinion, depends on the manner in which the relationships were developed. We know that consolidation curves have a characteristic shape. They don't suddenly take jumps. We know that the steady state line has a characteristic shape, and it doesn't suddenly take jumps. And the extrapolation process is guided by the relationship between the apparent steady state line and the consolidation curve. So if our procedure respects the soil mechanics principles and is consistent with steady state behavior, we can extrapolate to some degree, I think, reliably. And so with my procedure, I'm willing to go out to perhaps blow counts of 17 or 18 blows per foot, but I have a difficult time justifying going beyond that. In our statistical procedure, the uncertainty would increase quickly as you go out to higher blow count levels. And so if you're doing a probabilistic analysis, you have to account for that uncertainty. Even if you're going to treat it deterministically, you might say, okay, I'm going to use in my analysis a residual strength that has a 10% probability of being conservative, or not being conservative, or 5%. You make that kind of a decision, and that uncertainty level would push the residual strength down out at those higher blow count levels. It's a difficult problem. It's a problem that I'm asked about frequently, and I think that by acknowledging that the steady state line is steeper than the consolidation curve, and assuming that you don't have extremely unusual situations such as water flowing into a reservoir, or soil flowing into a reservoir, a body of water, where you get hydroplaning, or some other very unusual conditions. If your conditions are approximately similar to conditions in the database, you can extrapolate a little bit. If I was using the ones that assume proportionality, I would not extrapolate very far.